So far, so good. Who knows what's going to happen over half an hour. So we are looking at NIOManager. We saw the API, and we wanted to understand how the API actually works underneath. That's the whole point. API, you've used, and it seems. So what's going on underneath at one level is that we have command objects, and for each kind of operation, you have a separate kind of command object. Regardless of the kind of command object, it's enqueued. And when it's dequeued, it's enqueued by the process that wants a service. And the dequeuer is a selection thread. And when it dequeues it, it goes and calls the initiate method in it. Then the initiate method will set an appropriate interest op. And then the selecting thread will go and invoke a select call to block on whichever operations are of interest, and it'll come back and it'll check which kind of operation, which operations are enabled right now, and for each command object associated. So for a command object associated with each operation, it calls the appropriate execute method. Okay, so it calls execute methods only on those command objects associated with operations that have been enabled. Okay, you initiate only once, you execute multiple times. Connect, you initiate and execute only once. And in the case of read also, we'll have only one read command object that's always around. Okay. So also we want to not mix reads and writes. Okay. So let's go and see how this stuff works. We actually saw it last time. Just because we lost the recording, I'm going to go through this again. And also we'll go through the logs in a little bit more structured way. So there's the observer pattern that is implemented by all these command objects. Okay, so whenever the execute operation is invoked, it invokes listeners. It invokes appropriate methods on the listeners. Okay, that's standard stuff, so I'm not showing you that. Okay, but the main point is that in the initiate method for accept, it goes and says, okay, I'm interested on this channel in the accept operation. Okay, so this is a server socket. It'll always be enabled with accept. So we have to do this only once, and when the accept operation is ready to execute, that means a connect message has come in. Okay, the execute method will be called, which will go and invoke the accept method on it, get back a channel. That channel needs an interest op. That interest op was passed as an argument to the constructor of this particular thing. So that is the so next op doesn't correspond to this particular channel. It applies to the new channel that was created. Okay. So we see this here. So this is a tale of two threads. Okay, the main thread and the select thread. Okay. So we'll try to follow each thread. So the main thread goes and says accept. Allow listenable accepts. Okay, so it says whatever happens underneath, I don't care. I just want listenable accepts. So what's happening underneath? Okay, it goes and says, okay, in the constructor, it says, let's see what your next interest op is. So when the accept does succeed, I want to know what the next interest op should be for the new channel, and that happens to be 1. Okay, which is read. Then it goes and enqueues that. The main thread enqueues that in the queue that will be read by the select thread. So let's see what the select thread was up to. The select thread before that, this independently went and called select and was blocked. Okay, so the main thread, after enqueuing, goes and wakes up the thread. Okay, so the thread gets woken up, unblocked. I haven't underlined that, and it then dequeues the command. And it goes and configures. The configuration is left to the accept command. So accept command can decide whether we want blocking or not blocking. So it decides that it's going to be not blocking. And then it goes and registers this particular channel that was created by the main thread with the selector object, saying, when I block next for select, I want to be told, I want to express an interest in this channel and interest in the accept operation in this channel. Okay, and now it's going to go in, and this is number 16. So this is the accept op. Okay, again, there are 2 interest ops involved here: the interest op for the server channel and the interest op for the new channel. Okay, so since this is an accept command, it has to be, that was not passed as a parameter. This 16 was not passed as a parameter because accept command is bound to the accept interest op. Okay, so that is the interest it expresses. And then it says, okay, wake me up when, and again, ops1 was what was passed. So they're two different things. Okay, and ops1 was passed because appropriate factory was set. So the reason we got 1 for the new channel is because we set an appropriate factory. Again, those of you who finished the assignment know that that's what you did. Okay, set a factory. Now the next ops apply to the same channel. We were first listening to connect on it. Now we listen to something else. It may be write or read. Okay, it better not be connect. If you make it connect, it'll always return true, saying, yeah, you're already connected. So if you're interested in the connect operation, the select will just keep unblocking. Okay? And I didn't know that. I thought you'll get to that only once, except that when I put the tracing on, I just saw a lot of connect. I saw that this was going through in a loop without interruption. Okay, so let's go with the connect trace. Very similar. You don't say enable accepts. You say I'm requesting connects. Okay, and notice that the channel at this point is unconnected. Okay, so when you first create the channel, it's unconnected. Okay, and you expressed an interest in this. This is the main thread. The main thread enqueues a request. This time it's the connect request that's being enqueued. And so I said that the connect command is singleton. It's not really a singleton. I misspoke there. For a particular channel, you'll have only one connect command. But the selecting thread can be dealing with multiple channels. So you could have multiple connect commands for different channels. Same thing with accept. Same thing with read. Okay, so they're not really singletons. It was loose. In terms of programming language, that was loose. In terms of, it's just, I want to say that for each channel, there's only one instance of this. Okay? So you still have a queue, but that queue has multiple, is partitioned by, can be partitioned logically by channel, in which case the queue has only one element. Okay, so the select request is dequeued. And at this point, the initiate method is called. Now we're not just doing interest op in the initiate method. We're also doing connect. We're sending a message to the server. This operation will succeed. There's immediately, and there is a buffer for it. So we don't have to wait for this operation to complete. Okay, so we can initiate connect, and now look at our connect status. It's connect pending. Okay, so we were disconnected and now it's connect pending because we sent a message to the server. Okay. Now we are waiting, and we're waiting for the message to come back from the server. That is the connect op. Okay, so we go and tell the server, hey, interest op is 8. 8 stands for connect or finish connect really. And, I forgot about this one. So, we guys get involved in programming, and it's hard to, it's addictive, right? So it tells me, go look somewhere else. Don't let your eyes dry up. So it's wonderful, by the way. I recommend this to everybody. Okay. Of course, I just ignore it all the time. So, but at least I'm feeling guilty when I ignore. Feeling guilty is better than not feeling guilty. Right? So, and after 45 minutes, it'll just blank the screen, actually. Okay, so I have to leave this. So, okay. So we have expressed an interest in 8. Now we go and call select. Okay, this V meaning the select thread says I'm waiting for a message to come back from the server. When the message arrives, you unblock, and the socket channel is connected at this point. Okay, so you see the status. We are connected to this particular location. Okay, and now we are saying, okay, we are connected, so we are changing our colors. The same channel now, we don't want to wait for connect on, we'll wait for something else. That something else was passed to the constructor through the factory, and that happens to be 0 in this case, which means read. Okay, and that was passed, done through the factory. Okay, I'm going through this maybe too fast, maybe too, we did this before, so in that sense I'm going through it a little slow, but now I've got these underlines, and then hopefully this recording will survive. So, okay. Okay, and then we finally call select. And you do the select on this one. Okay, so let's go to write. We see the pattern here. Initiate registers interest op. In the case of connect, it also went in sent a connect message. Execute does the operation. So we might follow the same pattern here, except we won't. Okay, because we want to problem of write gather. Okay, we want to do all the writes at one shot if we can, so that we send only one message across. And also, my understanding of the Rocks tutorial was that we shouldn't mix reads and writes. Okay, it can cause problems. So what we'll do is we'll have a composite command object, and that's a design pattern too. Again, my 401 students who I taught so carefully have forgotten about command objects, and have forgotten that you actually create composite command objects. So you guys actually created a command object for the repeat command, which went and called execute methods on the commands that have to be repeated. Okay, so there's actually, this is a pattern, and we'll use this pattern again here. And that pattern will be part of a bounded buffer. We'll have now a write command with no initiate. I mean, the write command I have implements the initiate interface, but initiate does nothing. Okay, so effectively there's no initiate. There is execute though. So initiate method gets bumped up to the parent object. So there's a write bounded buffer. Now that's in the composite command object. Okay, we didn't have that for the reads. We didn't have that for the connects and accepts. But for the write command object, we have a bounded buffer into which all the writes go, so that they can be done one after the other after one unblocking of the select. Okay, and the execute method. So the write bounded buffer has references to the write command objects, and the execute method invokes the execute methods of the child objects. So the initiate method is invoked in it at the beginning of the loop. Okay, so before the select thread is going and executing the select operation multiple times in a loop. Before the select, it goes and checks, looks at the write bounded buffer, sees if it is non-empty. If it is non-empty, it says, okay, I'll call your initiate method, and you decide what your interest ops need to be. And it says, okay, it should be right. And then after the select call, it goes and sees whether there is any write enabled. If write is enabled, it goes and checks if the bounded buffer has any object queued in it. If it does, it calls the execute method on the bounded buffer. It doesn't know what's going on underneath. As far as it's concerned, that's like one object. The write bounded buffer goes and calls execute methods on all the child objects, and it keeps calling the execute methods until it can't write anymore, or I heard the other answer also, until all of them have been executed, whichever happens first. Okay, and each time a write occurs successfully on a command object, it dequeues that from the bounded buffer. Okay, so a lot of stuff going on underneath the cover. That when initiate is called, you go and register interest in the write operation. Okay, or you could go and do saved interest ops, whatever was the previous interest ops, or write. Okay, and if I was a little less scared about the implementation, I would do what I just suggested here. So let's consider the pros and cons. I want to write, what I'm doing is the following. Let's look at the code. Let's look at execute. Okay, what is execute doing? It goes in a loop, calls a child execute. If the child execute is successful, it keeps doing the execute. If it's not, it returns and says returns false. Okay, I really didn't need the else there in the first if, because I'm returning false. Otherwise, it removes the child, and then it goes and execute again. So it's not doing selects in between. Okay, for after unblocking and finding there's enough space, it goes and says, let me write as much as possible in this available space till I run out of space. So I am not mixing reads and writes here. The question is, when I run out of space, what do I do? At this point, should the selecting thread wait only for write, or should it wait for write or anything else? What do you guys think? It went and wrote as many buffers as possible. Now it's run out of space. Okay? Since it's run out of space, it's going to say, okay, let's go and call select again. Before I call select, let me go and, I'll call all the initiate methods that need to be called. And those initiate methods together should figure out, what the interest of should be. Okay? And some initiate methods I won't call multiple times. Okay? It's only if the object is queued there. So if the buffer is not empty, should this initiate method say, I'm interested only in write, or write in anything else that was of interest before the writes were submitted? What do you guys think? Yeah.
Anything that was of interest before too, because you can be, other things can be happening.
So you're reducing concurrency.
Yeah.
And it can be actually really bad. It's possible that you run out of space and you'll get back space only if you process some incoming message. It's possible that that space release depends on an incoming message arriving. And you are not even processing the incoming message. You're not even receiving, you're not, for instance, processing or doing a read. Okay? So you're blocked on this write and you're not doing anything else. And that may actually free up some space that will allow you to proceed. Okay? So this is not ideal. Okay, that's why I said I would rather go and do this, but hopefully, fingers crossed, and the space won't run out and this deadlock situation doesn't arise. And like I said, I was, my NIO knowledge came from this tutorial, and my understanding of the tutorial was that don't mix these two things together. So I followed this. But the architecture we have, we can go and replace this command object with another command object that is more aggressive. Okay, so which is a nice thing. Okay, and also when the buffer is empty, we go and notify the buffer empty listeners. They can go and change the interest stop at that point. So in fact, my original implementation did not save the original interest stops. It expected the buffer empty listeners to go and change back the interest stops. But I figured this is better default behavior. Again, after all, this is default. This is not cast in stone. Okay, because these command objects can be changed. So we go in, there are two write requests enqueued, 1, 2, for the header, which was done by the system, and the actual buffer. Okay, and then the selector is woken up. Okay, and it's unblocked. We go and set the initiate method is called on the bounded buffer. It goes and says, I'm interested in ops 4. And then we call select. Okay, so we know that there's a buffer in there. We've expressed an interest in the right operation, but we're not going to be we're not going to expect there to be actually space. So we say, okay, let's call select. If there is space, we'll get woken up. Okay, we call select unblocks because there is space, and now you go and write the header header in one write, and you dequeue that header request. Then you do the other write, you dequeue that, and now at this point the buffer is empty. So we go back to the original ops, which was 0, and we go and call the listeners that are interested in the write buffer being empty, and that's it. Then another issue we looked at was the client of this object provided us with a buffer to write. What should we do? Should we copy the buffer And the client did not wait for the buffer to be written. Okay, the client says, here's the buffer, I'm not going to wait, you write it. So the bounded buffer object could copy the buffer that was given to it, or it could just use that buffer. And what are the pros and cons?
Scalability.
Sorry?
Using a new buffer every time, or copying the buffer is a scalability issue.
It's a scalability issue, it's an efficiency issue. I told you I used to see so many papers in the Premier Operating System Conference all about making buffers efficient. Okay, and what's the con of this? Efficiency is the argument for not copying, and what is the argument for copying?
The client may want to reuse that buffer. And so-
Client may want to reuse it, or it may reuse it,
Yeah, they just get rid of it.
so it's not safe. Okay, so sometimes safety and efficiency, you get into a car, you go to waste time putting a seatbelt on, so it's kind of that kind of stuff. Okay. But they don't always contradict each other. Sometimes you can get them. You can get both. Okay, and that's the fun part. Or sometimes you can get a sweet spot, and so that's the fun part about designing things. So is NIO write buffer a copy of application send buffer? If we do that, there's no need for app to do buffer management, but copy is inefficient. So by default, we'll make not copy. And if the client really needs to use that buffer later, let it do the copy and pass us a copy. Okay. Okay, so application buffer not copied, and there's an object layer on top. Those of you who do the serialization assignment, you'll see that you'll be doing your own buffer management there, and you'll be supplying buffers to this particular layer. Okay, so pros and cons means we should have our own command object sometimes. So this is sort of, I'm just saying that's why we want flexibility. What about header information? What should be this naive approach is for each new object buffer that is to be written, we create a new header object. Okay, and the disadvantage there is we've allocated space. And how did we get over this problem? So this time we don't have a buffer from the client. This is okay.
Buffer pool.
Buffer pool. Okay, we had a buffer pool, and that means it's a finite pool. We may run out of header buffers, so Okay, so I think we stopped at this point. What about input buffer? Should we be sending a copy of the buffer we read to the application, or should we be just sending it the buffer into which we meaning the select thread? The select thread reads the data on behalf of the application threads.
I mean, like in our implementation, you mentioned we should, because in our case, the selector thread only has that one buffer.
So that's what it does.
Yeah, we have to make a copy.
You have to make a copy, right? But I could have created a copy and saved you guys from making the copy. And why didn't I do it?
I mean, I guess that way you can decide what actually gets put in the, because that way you're only getting a byte buffer. Like if we wanted to pack it some other way for the client to read, I guess there's a little more flexibility there on the client end.
Yeah, you guys, I told you guys to create a separate thread. Maybe you could use the selecting thread to read the value. Okay, so in your case, there was danger. Okay, because things were getting buffered. But if the select thread could be used to do the processing, okay, then maybe why waste the copy? Why waste time copy? Okay, so again, by default, don't copy. And if the client needs to, it can copy, either when it's writing or when it's reading. Okay. So is listener buffer a copy of an IO read buffer? Listener can manipulate its contents if it is, but copy is inefficient. So there is a single input buffer with complex I think I've got another slide on this thing. Create an input buffer for each logical write that's been written. Okay, so each time we read the header, we read the rest of the stuff in one message, in one buffer. When we figure out that we've read enough, we go and we go and create a new buffer for the next read. Okay, or we could create a single buffer for all writes. Okay, so remember the writes are coming to us in header and data pairs. I could create a separate input buffer for each pair, or I could create a single input buffer for all pairs. Okay, and by now we know the story. Okay, fewer buffers, less copying, more efficient, and so should we create new input buffers for each send output buffer, header data pair? Inefficient. It might make the scatter gather code easier. Okay, that was very tricky code to implement. By the way, I do have from a previous class recorded lecture on how exactly I do scatter gather. So when I create the videos for this, I'll go and put that also somewhere there. You won't be responsible for learning that stuff, but just in case you're curious. Okay. So there's actually a single input buffer with complex scatter gather. Okay. So what can happen is that the buffer that the selecting thread has read into may have more data than is of interest to the listener. I might have part of the next message in it, next data in it. Okay, because they arrived, 5 buffers arrived together. Okay, and I want to deliver this one by one. So I might have more data than is to be consumed. So can I deal with that? Can I have my cake and eat it too? Can I really have only one input buffer? So the client went and sent 100 commands at one shot. Okay, 1,000 commands at one shot because the professor says go and do that. Okay, and only one message was sent, and now we want to deliver in listeners those 1,000 messages one by one. But we've read them all. A single write has gone and read the whole data. So can I actually have only one buffer? Given that the read listener is supposed to is expecting only one message at a time and not the whole thing.
Do these messages get does the header have information just to say this is the start? This starts at command 1 and then ends at command 50, or does it?
No, remember, the header doesn't know command 1 or command 50.
That's what I was asking. It just says.
Header just says the next piece of data is this long. Whether it's a command or whether it's something else, who knows? So each header corresponds to says that's what I'm. But it just talks about the next data pair. Mm-hmm. But you as an application went and sent 1,000 commands together, and they all got packed into one message. It was read as one message at the other end. Okay, so now I have to go and break it up into pieces so that the reader can get each of them at one time. So do I have a problem? I must not. It works.
How do we parse that into different messages then? Like if the header has no information of
No, the header has. The selecting thread knows through the headers exactly what those chunks are.
Okay.
Selecting thread knows 5 bytes here, 10 bytes here, 15 bytes here. It can know. The only problem is that it's gone and read the whole thing at one time because that's what arrived. It read the whole thing, it broke it up into pieces. Now it's got to go and deliver the pieces to the read listeners. And we have only one buffer. So can it really break it up into pieces without copying, is my question. It has the information. And this is the byte buffer object in Java. A byte buffer object is not an array.
Yeah, we can do it without copying because the byte buffer just allows us because we just move down we have that position, the start position in the length, so we know how far we need to grab for each message. So we just keep moving down the byte buffer.
So the byte buffer is an array plus some pointers. I can have 2 byte buffer objects that share the same array. So I won't copy the array, which is what the real data are. I will create new byte buffer objects that will just go and change the view that is seen by the client. That's why the byte buffer object is so cool. Okay? Okay, it could be non-zero. Okay? So what's happening with read object, read? The initiate method is kind of, yeah.
I have a question that kind of goes back to assignment 1 and semantics of that. So if we were to call like bytebuffer.array, because like whenever the socket channel reads, and we say like bytebuffer.array, do we get, or I think you call it like a message, like if we have the socket channel read, does array give you that full backing array, or is that only the length of the, or does it only give you like the length of that message?
Array gives you length or it gives you the array?
I mean, does it give you the like just the little, like the pointer to that one, the multiple byte buffer sharing the same.
Okay, so in general, I don't remember the names of the operations, but there are two kinds of operations. One that just gets the data, and the other operations get you various information about the pointers. Okay, the one that gives you back the data will give you back the whole array.
Okay, because
It won't go in. It's not like C, which it'll just go and add an offset to the and gives you an array from that point onwards. Okay.
Like if you have, since the byte buffer points to this section of the byte array, if you were to call, I guess I should probably just look this up in the docs. I didn't know if...
No. Don't have to look at the docs. You can reason this out.
Okay.
I never look at the docs. I always reason it out.
Because I realized in my assignment, whenever I create a new, like, the processor takes a string. So whenever I read, I say C byte, or like the buffer, byte buffer.array.
Yeah.
Okay. Does that give me just the section that byte buffer points to of that full backing array, or does it give you the
So
entire
that's what I'm trying to tell you, that in C, I can take an array and create multiple arrays out of it.
Yeah.
I can go and say, this starts from 0, let's go and add address 10. I've got a new array now. In Java, you can't do that.
Okay.
So you only get, if you create an array from 0 to the particular size, you can only get the address to the 0th byte. You can't just add addresses and create sections of it. Okay? Because then the question is, what's the size, what's the length of it, where is that length kept? So you're always getting the full backing array. Okay? If you want to go and create a copy of that, you can use the pointers and the backing array to create a new array. Okay? I don't remember whether the array operation is a copy operation or not. There are copy operations that in the deep duplicate stuff,
Is deep duplicate a copy like
that's
that?
copy, absolute copy.
So then that's because I just realized like if that's the case, like there should be issues that like if I'm getting that full backing array, I should never process this. But I noticed I never actually had any issues.
Yeah, no. The deep duplicate is not only a duplicate; it's a deep duplicate. So a duplicate will copy the array, and a deep duplicate, does it. Yeah.
Gives you the appropriate pointers.
Yeah. Actually, no. Deep duplicate is the one that will copy the array. The other operations will not copy the array. Yeah. Okay. Okay. So in no initiate method here, some other operation is going to decide whether you want it to be readable or not. Okay. We saw that the connect operation decided it. The accept operation decided it. The write operation decided with the saved address op. So the initial method is ignored here. I've got a typo with Boolean. But what it's going to do, it reads whatever it gets, then it extracts the appropriate next chunk, okay, from the read data, and notifies the read listeners, and then it sort of does that in a loop. So I should have really had a loop here, but it basically loops through and extracts as many messages as possible with this one read, and invokes the read listeners, and then goes back to waiting for more reads or the next operation. Okay. So this is part of a loop. This.
In this case, how are the next operations handled? Because your constructor only takes the channel, so you can't define what that is.
So we don't.
Yeah, it's always just reads then.
It whatever it was. Read yes. So somebody else is deciding on whether it's readable or not. We didn't do. The read command object never does that. Okay. That's just one way to do things. Yeah, I don't know why I highlighted this one. So, oh yeah, we read the data part. Now we read, so that line is just a little off. Is there a header read somewhere here? Yeah, yeah. So my line is a little off. So I've got the header read, then I've got the full data read after that. Okay, so even though only one read occurred, I broke that up into two chunks, and then I called one listener for in response to that. Okay, and then I go back and start reading things. Okay? Questions? So, our saga of NIOManager is finally, or NIO is more or less over. Okay? So we've seen how this API works to create depth. And let's try to back off now, back up a little bit, and try to see the big picture. So way back when we were doing interrupts, which seemed totally unrelated to this stuff at one time at least, we saw that there was the notion of a upper half and a lower half. Okay? Upper half is what gets executed in the user mode. It can be either doing reading or it can be doing writing. In either case, it's requesting operations to be done by the lower half, the kernel. Okay? It doesn't really do the operations. It doesn't muck around with device registers. It doesn't read them. It doesn't write to them. It enqueues requests. So if you're doing a get, it says, hey, I'm interested in a get. Block me till I get some data. If it's doing a write, it says put. It says write my stuff, and that's not going to block it. It'll block me if the buffer is full. Okay. So that's the architecture. Now, can you guys see an analogous architecture with NIOManager? NIO on its own is just an API. But with NIOManager, I'm kind of hinting that I mimic this architecture. So if I mimicked it, what corresponds to the lower half and what corresponds to the upper half? The NIOManager is the lower half, and your code is the upper half. So that's one way to look at it. Good. Now I want to sort of argue that the upper half, lower half is not just a layering thing, it's also a thread thing. The upper half is sort of one thread, I would like to say, one asynchronous agent, and the lower half is another asynchronous. So these two agents execute asynchronously. So if I say that, what's the lower half? The selecting thread. Okay? And the upper half are the, even in operating systems, the upper half can be part of actually a kernel routine. So when you do get, you enter the kernel, you execute in the kernel mode, but you're executing as your thread. It'll go and enqueue a request and it'll block, and then the lower half will be another thread. Okay, so we call this the upper half and lower half of the device driver, both of which actually exist in the kernel. So I kind of misspoke earlier, implying that only the lower half is the kernel. Okay, so same thing here, that you went and executed in the upper half in the NIOManager code. That went and enqueued information for the selected thread, and then in our case it just returns. It doesn't block because we are NIO. Okay, and the lower half is a selecting thread. Right? I've got a dangling consumer there which I'll try to get rid of. So what's the analogy with NIOManager? I'm so paranoid. I did say click. Okay. Lower half executes in selection thread, gives commands to lower half. So command objects are the requests, processes request. Okay. And in the lower half does things like identify channel and buffer and post-operation interest ops. And the lower half registers, selects issues, writes, calls listeners. Okay. And so this is sort of the communication. That's what's going on in between. So that's graphically what I just said. And the synchronization, what kind of synchronization do we see here between these two asynchronously executing halves? Okay, so that's alerting the listeners occurs in the same thread. Synchronization is something that occurs between threads. So if my command request is full, what happens to the upper half stuff? It blocks. It can block and it does block. Okay. Does the selecting thread ever block? We know that the lower half interrupt handlers never blocked. Does the selecting thread block? When it calls select. So let's try to figure this out. There's an analogy between selecting thread and the lower half routines. Lower half routines never block. The selecting thread blocks. So what's going wrong here? Why do we have blocking here when we don't have blocking at the lower level?
It's only blocking when it doesn't have anything to do.
It's only blocking when there's nothing else to do. That's fair. But when it's waiting for new events, it waits for them by blocking. How come the CPU doesn't block? How come the lower half routines in our kernel don't block? Why don't we have, yeah?
They can context switch to other programs?
They can context switch to other programs, that's good. But somehow, there is some information we want to know about, right? We want to know whether an operation got ready at a higher level. In the interrupt routines, we want to know whether my output device emptied the last buffer, whether my input device has some information or not. How am I getting those events if I'm not blocking? So what happens when the device gets ready?
The system
Interrupts. And how is interrupt checked for? Those of you who did an architecture course? Cycle stealing? You guys studied cycle stealing? So after each CPU cycle, the CPU goes and checks the interrupts. That polls. There is no such thing as getting away from polling. Okay? The question is, at what level are you polling? We want to poll only at the lowest hardware level. We don't want to poll in the browser or other levels. Okay, so this is after each cycle, it goes and quickly checks if there's an interrupt or not, and then comes. Okay, so that is why we have to go and call select. Okay, but besides select, should the selecting thread block on any operation other than select? That's dangerous, right? That's like the interrupt routine blocking on something. So, okay, so the way the synchronization occurs is that, the upper half will block on full queue, and it'll wake up selector to unblock it from the select call, and upper half blocks in selective queue is empty, okay, and blocks in selective queue empty. So any events at all, right? So should listener method be okay? So we go and say the only blocking call selection thread should make is select, and it should execute efficiently. Okay, so execute as quickly as possible. Don't waste time. Don't wait for the simulation to be updated, and that is why I had you guys implement your separate reading threads. Okay, I didn't want those reading threads to be doing complex things, reading operations to be done in the selecting thread, because the operations can be complex. Okay, so now you see the rationale for that rule. Plus, I wanted you guys to get practice with producer-consumer problem. Okay. 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 I guess I'm trying to say here that the selecting thread, if it gets delayed, processing for other threads can get delayed. Okay, I think the text here doesn't make sense to me right now as I read it. So I think what's going on here in the text I've written, the second line should be blocking done by some application threads, okay? So the only blocking call selection thread should make is select, and yeah, the other application threads can unblock it by doing wake up. But if there is any blocking to be done, application thread should do it. And otherwise, you could be starving application threads if the selecting thread itself is blocking. Okay. So application listeners should not block or take too long as they delay or starve some other threads. That's the point here. I don't. The light blue stuff is making not much sense to me right now. Okay. And again, by default, I don't go and execute the listener in a separate thread, because who knows? Maybe that listener is just going to say "Hello World." In which case, why did we go to the overhead of having a bounded buffer, having threads? So, we went for efficiency again. Okay, if you make the normal case or make it possible to have efficient code, and so that's a rule being followed here. Maybe not. Okay. So if we do need to block, use a thread pool like you guys use a separate thread or a thread pool. Okay. So NIOManager does not use new thread to avoid thread overhead when not needed. Okay. Belaboring this point, I guess you won't forget it. I don't have to have a quiz now on this.